In the last lecture, we defined the notion of an abstract group. We had earlier worked out some of the properties of sets of symmetries in any particular context, and we took those properties and we said that any set equipped with a binary operation which satisfies those properties as a group. Now, what we will do is we'll derive some properties which can be derived from the group actions. The group actions are those three properties that we said that the binary operation must satisfy. So these are properties that all groups will have. They're properties that simply depend on the algebra that is forced upon us by the group actions. They will not have anything to do. So if your group happens to be the group of symmetries of something, they will not have anything to do with the particular properties of that object. These are just things that are following from the algebra. Okay, so recall that a group is a pair G comma star, where G is a set and star is a binary operation on G, having satisfying certain properties. So this is not how I had stated it in the previous lecture. I had worded it a little differently. I had said G is a set along with which is equipped with a particular binary operation. Here I'm saying that the group is actually the pair G comma star. So this is just to emphasize the fact that when I say group, I'm not just talking about the set. It is the binary operation is part of the group. Without the binary operation, there is no group. In fact, if I take the same set and I impose two different binary theorem, but still I'm just showing you that if you have sometimes if you have a particularly weak hypothesis, it just increases the power of the theorem. We will see this later on, actually today itself, in the next result that we are going to look at, and this is about inverses. So the axiom about inverses only states that for any f, there is some element which I call as f inverse, which has these properties that f times f inverse is equal to 1g and f inverse times f is equal to 1g. But we are not saying that the inverse is unique. We are only saying there exists some element. But again, we can deduce a stronger statement that we'll see that every element has a unique inverse. So this is our second theorem, that that G is a group and F is an element of G. Then H is an element with the very weak property that FH is equal to 1G. Then I claim that H is equal to F inverse. So notice that I did not even assume that HF is equal to 1G. I only assumed that FH is equal to 1G. So H behaves like the inverse from the right. So such a thing is sometimes called as the right inverse. I could have also assumed the other thing, that so similarly, if H satisfies HF is equal to 1G, that is, if H is a left inverse, it behaves like the inverse from the left, then H is equal to F inverse. So actually there is people do talk about such concepts, right inverse or left inverse, but in the when you're dealing with groups, it turns out that they are the same as the inverse, and so there is no need to talk about them these notions in the context of group theory. That's what this theorem tells us. So let's prove this, that let us assume that fh is equal to 1g and prove that h is the inverse of f. So h is equal to, well, 1g times h. This is just the property of 1g. Then 1g, I will write it as f inverse f, and I put brackets around it. This is just definition of inverse. And then I use associativity to move the brackets. Right now they are around f inverse and f. I move them around f and h. And then I assume my assumption is that fh is equal to identity. So this is equal to f inverse times identity, which is equal to f inverse. So the proof in the case when HF is equal to identity, where H satisfies the other equality, not this one, but the other one, then also we can deduce that H is equal to F inverse. The proof is quite similar, except that instead of multiplying H, writing H as 1G times H, I will have to start by saying H is equal to H times 1G. So again, as an exercise, you can write this out, particularly if you're not used to writing proofs. This is a particularly simple proof, so it may be good for you to write it out. Okay, now let's talk about so again, notice here, very weak assumption, right? I was trying to show that inverses are unique, but I chose to prove something much stronger, that any element with even just this simple property, rather weak property of just being a right inverse, then that also is actually the inverse. So what is the advantage? We will see the advantage here. So the question is, if A and B are two elements, what is the inverse of their product? So the inverse of the product AB is not equal to A inverse B inverse. In fact, what it is B inverse A inverse. The order matters, right? The order in which two elements are multiplied matters, and the claim here is that AB inverse is B inverse A inverse. So the proof is very simple. I just multiply things out and see. So AB times B inverse A inverse is, well, you just change where the brackets are. Initially, they're around B inverse A inverse. Put them around B and B inverse. Though that goes away and I get 1G. Now, what I do is I combine this. Maybe I should have put brackets around this. See, actually, I mean, I have not really written the whole thing here. Actually, what is happening here is that the brackets are around AB also. There are two sets. There should be two sets of brackets here. AB and then around AB and B inverse A inverse. Then what I'm doing is I'm writing a different set of brackets entirely. I'm putting a pair of brackets around here. Actually, again, here there are three elements in the picture. So really, I should be talking about multiplying, which way I'm going to multiply them. But the thing is that we already know the associativity rule, so which is why I chose not to litter the page with lots of brackets. But anyway, what is happening is that this B inverse goes away to give me 1G, which I then combine with this A, and then I'm left with just A times A inverse, which then again becomes the identity. And so what I'm seeing is that if I multiply AB on the right by B inverse A inverse, I get 1G. And then using my earlier result, I'm immediately able to verify, to conclude that B inverse A inverse is the inverse of AB. I did not need to verify the other multiplication. I did not need to multiply AB on the left by B inverse A inverse. So again, this is showing you that because I had a theorem with a weaker hypothesis, it made the theorem more powerful. It saved me some effort over here. Anyway, so um, in general, I mean, the reason why I'm even talking about this is that I want to drive home the fact that the inverse of AB is B inverse A inverse and not A inverse B inverse. These are two different things. Okay, so you can actually verify this, for example, in the dihedral group. Just check that if I take the something like rho square tau, what is the inverse of that? So you will first have to write the inverse of tau first. So that tau inverse of tau is just tau. So you will have to write the inverse of rho square tau is tau times rho to the power minus 2, which is just rho inverse squared. Anyway, so you can check that that A inverse B inverse and B inverse A inverse are different in the context of dihedral groups. It will be good to see it concretely. Okay, so just a little bit about notation, that if my binary operation is being written like multiplication, which we will often write it like multiplication, then we write f to the power n to mean that f is being multiplied with itself n times. So this makes sense when n is a positive number. But we will also use this for negative numbers. For example, if n is positive, I may also write f to the power minus n. What this really means is f inverse to the power n. And the thing is that this is just a notation. Now you can just make up whatever notation that you want with double meanings, and then but you have to check that it makes sense and it behaves as expected. So what the reason why we are writing it like this is because it gives us this simple rule that f to the power m times f to the power n is equal to f to the power m plus n for any integers m and n, not just positive integers, even negative. Now if m and n are negative, or if one of them is negative, one is positive, this thing holds. This is something that actually should be verified. You should check this, that this makes that this is correct. Nothing goes wrong. Okay, I could write out a complete proof which will be tiresome and will bore everybody, but the thing is that you should do it once for yourself. Not only will this be good practice for proof writing, you will also see that there is something to be written here. I mean, you have to train yourself not to make logical leaps. Your logic has to be followed one step at a time. You have to be sure of what you're doing at every step. You shouldn't just be guessing something and saying that it is true just because it seems likely. Okay, so it will be good if you're not used to that. It will be good practice to verify this. Okay, so now this is all I wanted to say about basic properties of groups for now. Let us look at something else. So last time I talked a little bit about this group, that the group of isometries of a non-equilateral isosceles triangle. What does that look like? So I had not talked about this in the recording, I think, but I had talked about this in the lecture in the classroom, that it is basically, it's only going to have two isometries. One is the identity and the other is the reflection in this vertical line. Those are the only ones. And what is how does this, so you can verify that these are the only ones. And this actually uses the fact that this is not an equilateral triangle. That's why I'm saying non-equilateral triangle. It's not going to have any rotational symmetries, and there are no other reflections also. So what does the multiplication table for this group look like? It looks very simple. There are two elements, and this is how they multiply. Tau times tau is identity. Tau times identity and identity times tau is tau. So it's very simple multiplication table. Let's look at another picture. The isometries of the parallelogram which has unequal sides and is not a rectangle. So it's a general parallelogram. It's got unequal sides, which means it's not a rhombus, and it is not a rectangle. So the angles are not 90 degrees. So in that case, you have very few isometries. You cannot really reflect in the diagonals because it's not a rhombus. Well, yeah, I mean, if it were a rhombus, you could have reflected in the diagonal, but it's not a rhombus, so you can't do that. Also, there are no other angles, no other rotational isometries, because I'm specifically assuming that the angles are not 90 degrees here. So anyway, the only non-trivial isometry you get is rotation through 180 degrees around the point of intersection of the diagonals. So that is what I'm calling as rho. And this group also has a very simple multiplication table, which looks very similar to the multiplication table I had earlier. The only thing that seems to have happened is that tau here is replaced by rho over here. But apart from that, I mean, it's really just that you could take this table, wherever you see tau, you could just write rho, and you get this table. So we could say that these groups are essentially the same. So I'm saying essentially and not actually the same, because they are not the same, right? Because one is the group of isometries of this non-equilateral isosceles triangle. The other is the group of isometries of a general parallelogram. As objects, they are entirely different. The elements are they stand for different things entirely. What is similar is that the algebra. The algebra looks similar, and we want to give a name for this, because, as I said, we are going to study groups as algebraic objects. They do have interpretations in many different contexts. They may have interpretations in geometry or something else, but we want to forget that context and just focus on the algebra. So as far as algebra is concerned, these two are behaving the same way. We want to give a name for this concept. So, but let's just look at yet another example. Here is a set which is this is a pattern which is supposed to be repeating infinitely in both directions. So I've got these triangular pattern repeating again and again. This is not an equilateral triangle. It's not it's it has got this one short side and one long side. It's supposed to be repeating. So it has got no other, and yeah, I actually meant these angles to be 90 degrees, but I think I didn't draw it properly later on. Just imagine that this is 90 degrees. So that this picture does not have any other symmetries except for shifting through this distance d. This distance d is supposed to be repeated over here. So you can shift this back and forth. It doesn't matter. You could shift it multiple times, but as in units of d, that would be those would be isometries. So the isometries are identity, or you could do sigma. Sigma is the translation to the right through the distance d, and so like this, shift to the right, or you could shift to the left, and that would be sigma inverse. Or you could shift 2 steps to the right, or you could shift 2 steps to the left. So you can write down all this infinite list. So sigma to the power I and sigma to the power minus I for all positive integers I. So and composition is very simple. It behaves very nicely as if these are exponents. Sigma to the power I times sigma to the power j is equal to sigma to the power I plus j for any integers j, whether they are positive, any integers I and j, whether they are positive or negative. So this reminds us of a group that we already know, which is the additive group of integers. Both these are behaving in the same way. So we would like to make this precise. What does it mean that they are behaving in the same way? And so that as groups they can be treated the same, as being the same. So we should say that two groups are the same if we can somehow match up their elements in a way that respects the binary operation. So what that really means is that I should set up a matching between them, so that if I take the multiplication table of one group and replace every element by its matching element, I should get the multiplication table of the new group, right? So of the second group. So this is what I'm going to make precise. So let G and H be two groups. So they have their own binary operations. So I've written two different symbols. For G, I'm writing the star, and for H, I'm writing this circle with a dot in it. So then a group isomorphism from G to H. So I'm not pronouncing the binary operations because, how do you pronounce this? But so this is basically a 1-1 correspondence from the set G to the set H, which satisfies this property that phi of x times G, x times y. So now I'm calling this times, but it's really star. So x and y being combined by the binary operation in G. First you apply the binary operation, then you apply phi. This is the same as first applying phi to each element individually and then combining them in H. So whether you apply the binary operation first or you apply H or phi first, you get the same result. This is what you expect this phi to satisfy. It respects the two binary operations in the two groups. Then you call, and it is a 1-1 correspondence. So it's a matching between them and it is respecting the binary operation. Then you call this a group isomorphism. So, okay. And if such a binary operation exists, if such a isomorphism exists, then we say that group isomorphism exists, we say that the groups are isomorphic. I'm not saying that the group isomorphism is unique. Okay, it may happen that there exists more than one isomorphism between two groups. In fact, very often it will be the case. But we just want to say that if there exists some binary group isomorphism, then we will say that the groups are isomorphic. So let us look at yet another example of isomorphism. So let R plus denote the set of all positive real numbers. So even though I've written plus, the binary operation on that is going to be multiplication, right? So if I take the positive real numbers, that is not a group under addition, but under multiplication, it is a group, because if I take two elements, two positive real numbers, their product is again a positive real number. It's never negative, it's never even equal to 0. Also, if I take a positive real number, its inverse, its multiplicative inverse is again a positive real number. So under multiplication, this is a group. And I'm going to write it as R plus, comma, dot. So dot is because sometimes we write multiplication as a dot. So then now I want to define an isomorphism of this group with some other group. So what I do is I fix a real number which is greater than 1. And then I define, well, actually, I don't really need this to be greater than 1. I even anything greater than 0 might also be okay. But the graph may look a little bit different then. So that's why I'm taking it to be greater than 1. Then the graph will look something like this. So it's going to blow up as you move to the right. It's going to go up very, very rapidly. If you go to the left, this is going to just taper off slowly like this. It will come closer and closer to the x-axis, but it will never actually hit the x-axis. It will just keep coming closer and closer, as close as you like, if you go further and further to the left. Okay, that's what the graph of the exponential function looks like. And this is actually a 1-1 correspondence between between the x-axis, which is horizontal. So it's a copy of the real numbers, and the positive part of the y-axis, which is R plus. Okay, it's going to set up a matching between them. This is a fact that I will just take for granted. I mean, we are not proving that the exponential function sets up a bijection, sets up a one-one correspondence between the real numbers and the positive real numbers. We'll just take it for granted. But what is of interest to us is that it respects the group law. So the group law in the real numbers, sorry, this I should have called this phi actually, because I'm calling it phi in the next slide. So this f that I have written here, it really was meant to be a phi. I hope that doesn't get too confusing. Anyway, so phi of x plus y is equal to, well, it is equal to a to the power x plus y. Now the property of exponents is that I can split this as a to the x times a to the y, and a to the x is just phi of x, and a to the y is just phi of y. And so phi seems to be respecting the group law. On the right hand side, the group law is that of the positive real numbers, which is multiplication, and here the group law is addition. So this is certainly respecting the group law. It's a 1-1 correspondence, and so we see that this is a group isomorphism between the groups. This is the group of positive reals under multiplication, and this is the group of all reals under addition. These are actually isomorphic. Okay. Now, what? So the group isomorphisms, they respect the group law. This actually tells us that they will also preserve the identity and inverses in a certain sense. That is to say, if phi is an isomorphism from G to H, G and H are groups, and phi is an isomorphism from G to H, then phi takes the identity of G to the identity of H, and it also behaves well with respect to inverses. That is to say, if I take an element X, I could take its inverse first and then apply phi, or I could first apply phi and then take the inverse inside H. Either way, I will get the same result. Okay, so these are simple properties. The proofs are very simple. So it goes like this, that if I take phi of 1g, well, I could write 1g as 1g times 1g. So this here, the multiplication is happening inside G. Now I can apply phi, and I can use that phi is supposed to be an isomorphism, that is, it respects the group law. So this is the same thing as phi of 1g times phi of 1g. And now in this equation, I can cancel out one phi of 1g from both sides, and I'll get that. So if I cancel it from the right hand side, I'll just get phi of one copy of phi of 1g. On the left, when I cancel it out, I get the identity element of H. Okay, because all this is happening inside H. So phi of 1g is equal to identity of H. This proves the first result, first claim over here, that phi of 1g is equal to 1h. Now take any element x of G and look at phi of x times x inverse. This is equal to, because phi is known to respect the group operation, group laws. This is equal to phi x times phi x inverse. Now the left hand side here is also equal to phi of 1g, which is equal to 1h, because that's part 1 of this theorem. And so phi x times phi x inverse is equal to 1h, and so phi x inverse is phi x is equal to the inverse of phi x, right? Phi of x inverse is equal to the inverse of phi x. This shows that phi respects, phi preserves identity in a certain sense, and it also preserves inverses in a certain sense. Okay, now let's look at another example. So as I said, when you create a new concept, you should see an example, and you should also see a non-example if possible. So let's look at a non-example. So let G be the group of rotational symmetries of a regular hexagon. So for a hexagon, we saw all possible symmetries. So in fact, we saw this for a general n-gon, a general regular n-gon, that it's got 2n symmetries. A regular hexagon will have 12 symmetries, but I'm only interested in the rotational ones. So that is, so a regular hexagon will have 6 rotational symmetries and 6 reflections. So the rotational symmetries by themselves, they form a group, right? Because you combine 2 rotations, you again get a rotation. So this is basically, okay, I think you know what I mean. So it's got 6 elements, and H is the group of isometries of an equilateral triangle. So this is this, both of them have 6 elements, right? There is the regular hexagon has got 6 rotational symmetries. The group of all symmetries of an equilateral triangle has also got 6 elements. Now, are they isomorphic? Right? Of course, as objects, there are two different things, but are they isomorphic as groups? So actually, they are not, and the reason is that their algebra is not the same. Okay, so what does that mean? So actually, I say that there are 2 ways to see this, but I'm only going to state one way, and you can think about the other way. Okay, that other way I will leave it as an exercise for you to think. So G contains a rotation rho through 2 pi by 6 radians. So rho to the power 6 is equal to 1G. Right? So this is and the other elements are basically going to be powers of rho squared, rho cubed, rho to the power 4, rho to the power 5, and then rho to the power 6 is identity. Also notice that rho squared and rho cubed are not equal to identity, right? Because rho to the rho is basically rotation through 2 pi by 6, which means 60 degrees. So rho square is rotation through 120 degrees, and rho cubed is rotation through 180 degrees, which is, none of these are identity operations. Okay, but there is no element with these properties inside H, which is a problem. So why is that? Because in H, that is the dihedral group D3, that is the group of isometries of an equilateral triangle, the elements are either rotations through 120 degrees or 240 degrees. In either case, if I take the cube of that rotation, I get identity. Or there are reflections, such that if I take the square of that, then it is identity. So for any element inside this group H, if X is the element, either X square is identity or X cube is identity. Right? Just make sure that this is you're convinced of this. So now if I have an isomorphism from G to H, then rho will map to something, but then that something, phi of rho, the square of that would be the same as phi of rho squared, and phi of rho cubed will be phi of, the cube of phi rho will be phi of rho cubed. Now the thing is that rho squared is not identity and rho cubed is not identity, so their images will also not be identity. So please convince yourself of this. We have not actually proved this literally, but we have almost established this, that if rho squared is not the identity, phi of rho squared can also not be the identity. Well, the reason is simple, because because what phi is supposed to be a 1-1 correspondence, so it can only map identity to identity. We know that it maps identity to identity. It cannot map any other element to identity. So since rho square is not identity, phi does not map rho square to identity. Also, rho cube is not identity, so phi does not map rho cube to identity. So the right hand side in both these equations is not identity. So these two elements also cannot be identity, but that is not possible inside H. Inside H, either the square, for every element, either the square or the cube is equal to identity. So this is giving us a contradiction, that basically what it is saying is that the algebra of G and H is fundamentally different. It is incompatible. There is no way to set up a 1-1 correspondence in such a way that the algebra is respected. So this is one way of showing that there is no isomorphism from G to H. So notice that this is a proof by contradiction, that you assume that something is true and then you show that something will go wrong. So many times we have to write proofs like this, and you should get used to it. You should see, the thing is that particularly when you're trying to prove that something doesn't exist, like here we are trying to prove that there is no isomorphism. So one way to do it would be to list out all possible 1-1 correspondences from G to H and verify that none of them is actually a group isomorphism. This is one way, which would be long and cumbersome. Sometimes actually it might not even be possible to write such lists out. Here only, because things are, both the groups are finite. They have finite size. That is why it might be possible to write out all 1-1 correspondences and see that there is none of them is actually a group isomorphism. But in general, when you are trying to prove that something doesn't exist, very often you will be writing down a proof by contradiction. Okay, so you should get used to this also. But as I said, there is yet another way to see that these groups have different algebra. So I'll leave it for you to think about it, and I will mention that in the next lecture.